What if I told you there is a place in the universe where 60 billion suns have been compressed into a single point? A place so massive, so impossibly dense, that it bends light itself into spirals before pulling it into eternal darkness. Somewhere out there, far beyond the reach of any telescope we could ever build, there exists a black hole that should not be possible. Yet it is. Its name is TON 618, and tonight we journey to the edge of what the universe allows. This is not just a story about size, it is a story about limits. About the places where gravity becomes so strong that time itself begins to break down, where the rules we take for granted stop making sense, and where light, the fastest thing in existence, becomes trapped in endless loops before vanishing forever. As we drift deeper into this story, you will discover how something this vast came to be, what mysteries it holds at its hidden core, and why it challenges everything we thought we understood about the cosmos. If this journey speaks to you, take a moment to like and subscribe. Your support helps us continue bringing you stories from the edges of space. And now, let the universe carry you gently into the unknown. Welcome to Sleepy Science Stories. To truly understand TON 618, we must begin at the beginning. Not at the black hole itself, but at the framework within which it exists. The universe is not a random scattering of objects, but an organized structure, a tapestry woven over billions of years. And within that tapestry, certain places become special. Certain locations gather more matter, more energy, more light. TON 618 occupies one such place, a cosmic crossroads where many streams converge. On the grandest scales, the universe weaves itself into something remarkable, a vast structure known as the cosmic web. This is a network of filaments and empty spaces stretching across billions of light years. It forms the pathways along which galaxies gather and grow. Imagine looking down on the universe from impossible heights. From this vantage point, galaxies appear like scattered lights in an endless night. But they are not random. They follow patterns, tracing lines and gathering at intersections. These patterns emerged slowly over billions of years, shaped by forces we cannot see, but whose effects surround us. The cosmic web is not immediately visible to us. We cannot step back and see it all at once. Instead, we must infer its structure from countless observations, from the positions of galaxies, from the absorption of light by intervening gas, from the subtle variations in the cosmic microwave background, the ancient light left over from the Big Bang. Each line of evidence adds another thread to the picture, until the web emerges from the data like a photograph developing in a dark room. Within this framework, matter drifts under the pull of gravity. It moves from the near emptiness of great voids toward denser threads. Then it flows along those threads into knots, where many galaxies meet and where brilliant beacons come to life. These knots are not separate islands. They are places where the flow of gas, dust, and stars has been strongest for billions of years. Places that build the conditions needed for sustained activity at galactic centers. One such beacon, TON 618, marks an extreme example in this landscape. It serves here as a reference point for understanding the widest context. The cosmic web reveals itself gradually to our instruments. Each new survey adds detail. Each new measurement confirms the pattern. Galaxies cluster along filaments like dewdrops on spider silk. The voids between them hold almost nothing, vast expanses where a traveller might journey for hundreds of millions of light years without encountering a single star. These voids are among the most mysterious features of the universe. They are not truly empty, but they are extraordinarily sparse. The average density of matter in a void might be just 1/10 that of the cosmic average, which means that in a volume of space the size of our Milky Way, there might be only a handful of small galaxies drifting alone in the darkness. These are lonely places, far from the bustling activity of the filaments and nodes. As the web developed from small irregularities in the young universe, regions that were slightly denser drew in more matter. Regions that were slightly emptier gave up their contents, and the contrast slowly sharpened. Sheets of galaxies formed first, then they elongated into lines and finally collected into nodes. This sequence left behind cavities so wide that hundreds of millions of light years can pass without more than a few islands of light. The result is a vast lattice, thin in most places, thick at crossroads, and always in motion. The formation of this structure began in the earliest moments after the Big Bang. Tiny fluctuations in density, imprinted during the first fraction of a second, grew over time. Gravity amplified the differences. Dense regions became denser, empty regions became emptier. The universe sorted itself, building complexity from simplicity, creating order from chaos. These initial fluctuations were incredibly small, just 1 part in 100,000, a barely perceptible ripple in the otherwise smooth distribution of matter and energy. Yet over billions of years, these tiny differences were amplified by gravity into the vast structures we see today. The cosmic web is proof that small beginnings can lead to grand consequences, that the universe has a memory stretching back to its first moments. Gas streams slide along the strands like slow rivers, guided by the pull of unseen mass that outweighs everything we can see. The streams end where the web thickens. These supply lines are crucial. Central engines at the hearts of bright galaxies need a steady delivery of fuel to remain visible across the observable universe. The quasar that anchors this discussion sits at such a junction, a place where inflows can arrive from several directions, where the depth of the gravitational well is enough to gather new material even as older material is heated and expelled. Think of it as a cosmic watershed. Just as rivers on Earth flow toward the ocean, gas in the universe flows toward the deepest gravity wells. And at the bottom of the deepest wells, black holes wait, growing, feeding, shining with borrowed light from the material that will soon disappear forever. The analogy to watersheds is more than poetic. It reflects a fundamental physical principle. Matter flows downhill in gravitational potential, just as water flows downhill in Earth's gravity. The cosmic web creates channels along which this flow is organized, directing matter from the voids into the filaments, and from the filaments into the nodes. At the bottom of each node sits a galaxy, and at the center of each galaxy sits a black hole. The whole system is connected, from the largest scales to the smallest. At this outermost scale, the details of any single galaxy fade into the statistics of many, yet the pattern itself becomes the main fact. Structure funnels matter, and matter pays that guidance back by strengthening the structure. Observers on Earth cannot watch the web directly in a single image, but they can reconstruct it in ways that agree with one another. Maps of galaxy positions reveal long chains separated by bare regions. Measurements of how light from faraway sources is absorbed at different wavelengths outline the same pattern. Together, the methods agree on long chains of structure and broad empty regions. The agreement is important because it sets a reliable frame for interpreting any single source. Different techniques paint the same picture. Radio surveys trace neutral hydrogen. Optical telescopes count galaxies. X-ray observatories detect hot gas. Each method sees a different component of the web, yet all converge on the same architecture. This convergence gives us confidence. The cosmic web is not an artifact of our instruments, but a real feature of the universe. The power of multiple independent observations cannot be overstated. When different methods, using different instruments, looking at different wavelengths, all arrive at the same conclusion, we can be confident that what we are seeing is real. The cosmic web has been confirmed in this way dozens of times over, using data from satellites, ground-based telescopes, and even computer simulations based on fundamental physics. The agreement is remarkable and reassuring. Spectral fingerprints from diffuse hydrogen trace cool streams. Counts of galaxies highlight where the streams end. Both point to the same intersections. The picture holds not only nearby, but also at great distance. This shows that the web matured early and has continued to guide how matter falls, how halos form, and how bright centers are fed. In that scaffold, the densest neighborhoods are more likely to host the brightest engines. Supply and demand are both satisfied there. The beacon considered here fits that expectation. The web also tells us about dark matter, the invisible substance that makes up most of the universe's mass. We cannot see it directly, we cannot detect it with any telescope, but we can see its effects. Dark matter shapes the web, creates the filaments, defines the voids. It provides the gravitational scaffolding on which visible matter builds galaxies and stars. Dark matter is one of the great mysteries of modern cosmology. We know it exists because we can measure its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more mass than can be accounted for by stars and gas. The cosmic web has more structure than could have formed from visible matter in the time available. All of these observations point to the existence of something we cannot see, something that interacts only through gravity. We call it dark matter, but in truth, we do not know what it is. It may be exotic particles left over from the Big Bang. It may be something stranger still. This mystery adds depth to our journey, reminding us that much remains unknown. Every photon released by that source must pass through the web on its way to us. Crossing the spaces between strands and threading sections of thin intergalactic gas, the journey takes billions of years. The web is not a rigid skeleton, but a record of motion. Matter trickles in along many paths and on many timescales, from slow infall of diffuse gas to the delivery of entire galaxies that fall toward a common center. Collisions and mergers stir the contents of the host. Some material settles into extended halos, some collects into disks, and some sinks further toward the middle, where the central mass resides. Along the way, the photons interact with the matter they encounter. They scatter off electrons. They are absorbed and re-emitted by atoms. Each interaction leaves a mark, a subtle change in wavelength or direction. By the time the light reaches our telescopes, it carries the history of its journey encoded in its spectrum. The spectrum of a distant quasar is like a diary. It records every encounter the light experienced on its journey. Absorption lines mark where the light passed through clouds of gas. The overall redshift records the expansion of space. The shape of emission lines reveals the motion of gas around the black hole. By reading this diary carefully, astronomers can reconstruct the entire path the light took, from the moment it was emitted near the black hole to the moment it entered our telescope. Each photon is a messenger, carrying stories from the distant past. Even when energy emitted by the central engine pushes material outward, the larger flows do not stop. The filaments reach far beyond the local environment and continue to replenish the surroundings. This balance between inflow and outflow is a key feature of the widest setting for any luminous nucleus. At large radius, the environment determines how often fresh gas is delivered, how much dust rides in with it, and how the host will respond as the center brightens or dims. When the outer reservoir is deep, the inner regions can be sustained for long periods. When the reservoir is shallow, the inner regions fade. Thus, the very existence of an extreme object at a galactic core points back to the history of its surroundings and the strength of its connections to the larger grid. The cosmic web operates on timescales that dwarf human comprehension. A stream of gas might take 1 billion years to complete its journey from a void to a node. A galaxy might drift for hundreds of millions of years before colliding with another. These are slow processes, patient and inexorable, driven by gravity's gentle but unyielding pull. To put these timescales in perspective, consider that all of recorded human history spans only about 10,000 years. The entire existence of our species is less than 1 million years. But the processes shaping the cosmic web operate on timescales of billions of years. To the web, the rise and fall of civilizations, even the birth and death of species, are mere instants. This perspective is humbling. It reminds us of our place in the cosmos, tiny and brief, yet capable of understanding processes that vastly exceed our own existence. The luminous host in view does not sit in a quiet suburb of the universe. It sits at a crossing where more than one filament can deliver mass. Where the density of neighbours increases the chance of encounters that can channel gas inward, the large-scale setting also shapes how we interpret the light that leaves the source. Foreground gas along the route imprints signatures that must be accounted for before the properties of the source itself can be isolated. Only by placing the source within the web can those imprints be separated from local signals. Understanding the web helps us understand quasars. It explains where they form and why they shine so brightly. It shows us that the universe is not uniform, but structured. And it reminds us that everything is connected. The cosmic web links the smallest scales to the largest, binding together atoms and galaxies in a single, evolving tapestry. This interconnectedness is one of the most beautiful aspects of modern cosmology. Nothing exists in isolation. Every galaxy is connected to the web. Every star is made of atoms forged in earlier stars. Every black hole grew from material gathered across cosmic distances. The universe is a unified whole, and understanding any part of it requires understanding its relationship to the rest. Ton 618 is not separate from the cosmos around it. It is a product of that cosmos, shaped by billions of years of cosmic evolution. The age of the universe when this light was emitted was younger than today by billions of years. This means the web then hosted more active beacons than it does now. The rate at which gas funneled into centres was higher. Finding an unusually bright source in that era is therefore not an accident. It reflects a network that was operating at high capacity and a node that was well connected. For now, the important point at this outer edge is plain. The universe provides highways for matter. Those highways deliver fuel to nodes, and nodes nurture engines that shine strongly enough to be studied from across cosmological distances. Among those engines, the source selected here stands near the peak of observed extremes, yet its place at a node of the web follows directly from the way gravity organizes the cosmos. The early universe was a more violent place. Galaxies collided more often, gas was more abundant, star formation rates were higher. In this environment, black holes could grow rapidly, fed by copious supplies of material channeled by the cosmic web. The quasars of that era were among the brightest objects ever to exist, beacons visible across the entire observable universe. Imagine the night sky as it would have appeared from a planet in that era. Instead of the sparse scattering of stars we see today, the sky would have been ablaze with quasars. Brilliant points of light, each one a galaxy with a supermassive black hole at its core, each one shining with the power of trillions of suns. It would have been a spectacular sight, a sky filled with cosmic beacons marking the locations of the most active galaxies in the universe. But it would also have been a dangerous time. The radiation from these quasars would have flooded space, potentially sterilizing planets and preventing the emergence of life. We live in a quieter, safer era, when most quasars have faded and the universe has calmed. At the end of this wide view, the placement of TON 618 within a dense knot of the cosmic web is the essential fact. It shows that the first condition for such a powerful beacon is met before any inner detail is considered. When moving inward from the broad cosmic web, the next perspective is the position of this quasar within the observable universe. Astronomers locate it at a distance of several billion light-years from Earth. This means that the light we see today began its journey when the universe was much younger than it is now. To observe an object at such distance is to look into the past. Light carries not only information, but also time itself across the expanding cosmos. Distance and time become intertwined at cosmic scales. There is no meaningful way to separate them. When we observe distant objects, we are not seeing them as they are now, but as they were then. We become witnesses to history, observers of events that unfolded billions of years ago in regions of space now unreachably far away. This temporal displacement is not a limitation of our instruments, but a fundamental feature of the universe. The speed of light is finite. Light travels fast by human standards, crossing the distance from Earth to Moon in just over a second. But cosmic distances are so vast that even light takes billions of years to traverse them. During that time, the universe changes, galaxies evolve, stars are born and die, black holes grow, and the space between objects expands. By the time the light reaches us, the universe it depicts no longer exists. We are cosmic archaeologists, studying fossils of light. The quasar appears faint in the sky, even through large telescopes, yet careful measurement reveals that its brightness is extraordinary. It outshines entire galaxies in visible and ultraviolet light. The fact that it can be detected at all from such an immense distance highlights how powerful its central source must be. Distances on this scale are measured through a combination of methods. The most common involves observing redshift, the stretching of light waves caused by the expansion of the universe. As light travels for billions of years, its wavelength lengthens, shifting toward the red end of the spectrum. The higher the redshift, the farther the object, and thus the earlier the time when the light was emitted. Redshift is one of the most powerful tools in astronomy. It turns every spectrum into a ruler, measuring distance across the cosmos. Each emission line from a distant object is shifted by a predictable amount, allowing astronomers to calculate how far the light has traveled and how much the universe has expanded during that journey. The principle behind redshift is elegant. As the universe expands, it stretches the fabric of space itself. Light waves traveling through this expanding space are stretched along with it, increasing their wavelength. Blue light becomes green, green becomes red, red becomes infrared. The amount of stretching is proportional to how long the light has been traveling, which in turn tells us how far away the object is. This relationship, discovered by Edwin Hubble in the 1920s, revolutionized our understanding of the cosmos and revealed that the universe is expanding. The quasar, associated with the central black hole under study, shows a redshift that places it billions of light-years away. This gives astronomers not only a measure of distance, but also a window into the conditions of the early universe. When the light now reaching Earth was emitted, galaxies were younger, closer together, and more actively forming stars. The cosmic web was denser and more dynamic. Gas was more plentiful and more easily channeled into the centers of galaxies. These conditions allowed black holes to grow rapidly and quasars to shine at their brightest. The universe at that time looked very different from today. Stars formed at a furious pace, galaxies merged and collided constantly. The night sky, if viewed from a planet in that era, would have been ablaze with brilliant quasars, far brighter and more numerous than anything we see now. It was a golden age of cosmic activity, a time when the universe was still young and vigorous. In the current era, the universe has entered a more sedate phase. Star formation has slowed. Most galaxies have exhausted their supplies of easily accessible gas. Quasars have largely faded as their central black holes run out of fuel. The universe is aging, settling into a long, slow decline toward a cold, dark future. But billions of years ago, things were different. The universe was alive with activity, and Ton 618 was one of the brightest lights in that cosmic fireworks display. The brightness of this quasar is not simply a matter of luminosity. It represents an energy output so vast that it dwarfs the combined light of all the stars in its host galaxy. This energy comes not from fusion in stars, but from the release of gravitational potential as matter spirals inward toward the central black hole. The process is so efficient that even a small fraction of the infalling mass converted to radiation produces an observable glow visible across billions of light years. To put this in perspective, imagine taking the entire energy output of our Sun and multiplying it by hundreds of trillions. That begins to approach the power radiated by this single quasar. It is a staggering amount of energy, all generated in a region smaller than our solar system, all powered by gravity alone. The efficiency of this energy conversion is remarkable. When hydrogen fuses into helium in the core of a star, about 0.7% of the mass is converted into energy. This is the process that powers the Sun and all other stars. But when matter falls into a black hole, up to 40% of the mass can be converted into energy, depending on the spin of the black hole. This makes accretion onto black holes one of the most efficient energy generation processes in the universe, far more efficient than nuclear fusion. It is this efficiency that allows quasars to shine so brightly. The light we detect has traveled for so long that the universe has expanded significantly during its journey. Space itself has stretched, carrying galaxies farther apart and lengthening the wavelengths of every photon. This expansion is encoded in the spectrum of the quasar. Each emission line is shifted toward longer wavelengths by a predictable amount, allowing astronomers to calculate how far the light has traveled and how long ago it was emitted. Every photon is a messenger from the past. It carries information about the conditions at the time and place of its birth. By the time it reaches us, the photon has been traveling for so long that entire civilizations could have risen and fallen during its journey. Yet it arrives intact, bearing its message across the void. Think about what this means. The photon was emitted when the universe was young. It began its journey across empty space, traveling at the speed of light. For billions of years, it moved through the expanding cosmos, threading the cosmic web, passing through clouds of gas, occasionally scattered by a stray electron but always continuing on. And finally, after all that time, after all that distance, it arrived at Earth, entered a telescope, was focused onto a detector, and became part of our data. That single photon connects us directly to the early universe, bridging billions of years and billions of light years. The distance also affects how we perceive the quasar's size and brightness. The farther an object, the smaller it appears, and the fainter its light. Yet this quasar, despite being billions of light years away, remains detectable. This tells us that its intrinsic brightness must be immense. Correcting for distance, astronomers estimate that the quasar radiates energy at a rate hundreds of times greater than that of the Milky Way. Such luminosity cannot be sustained by stars alone. It requires a central engine of extraordinary mass and efficiency, a supermassive black hole actively feeding on surrounding material. Astronomers perform these corrections carefully. They account for the expansion of the universe, the absorption of light by intervening gas and dust, and the effects of gravitational lensing by foreground objects. Only after all these factors are considered can the true brightness of the quasar be determined. And that true brightness is astonishing. Gravitational lensing deserves special mention. Sometimes, a massive object like a galaxy or galaxy cluster sits between us and a distant quasar. The gravity of this foreground object bends the light from the quasar, acting like a lens. This can magnify the quasar, making it appear brighter, or it can create multiple images of the same quasar. By studying these lensed images, astronomers can learn about both the quasar and the lensing object. It is a beautiful example of how gravity shapes light, and how we can use that shaping to learn about the universe. The position of the quasar in the sky also provides clues about its environment. It lies within a region of the universe that was rich in galaxies and gas during the era when its light was emitted. This fits the expectation that the most massive black holes form in the densest environments, where collisions and mergers are common and where the supply of fuel is most abundant. The quasar is not an isolated object, but part of a larger ecosystem shaped by the cosmic web. Its location in that web determined how much material it could gather and how quickly its central black hole could grow. Context matters at every scale. The quasar could not have formed in isolation. It required the right environment, the right conditions, the right history. Its position at a dense node of the cosmic web provided all three. The concept of environment extends beyond just the local neighborhood. It includes the larger structure of the cosmic web, the history of mergers and accretion, the availability of gas, and even the properties of dark matter in the region. All of these factors come together to create the conditions necessary for a supermassive black hole to grow. Understanding the environment is therefore crucial to understanding the black hole itself. Astronomers studying this quasar also observe variability in its brightness over time. These fluctuations reveal that the light comes from a compact region, far smaller than the host galaxy. The timescale of the variations sets an upper limit on the size of the emitting region. Light cannot convey a change faster than the time it takes to cross the source. For this quasar, the variability occurs over weeks to months, suggesting that the brightest emission comes from a region only light weeks to light months across. This is tiny compared to the scale of galaxies, yet it produces more light than an entire galaxy. The compactness of the source, combined with its enormous energy output, points unambiguously to a supermassive black hole as the central engine. Variability is a powerful diagnostic. It tells us not just that the quasar is bright, but how small the emitting region must be. Nothing larger than a light month across could change its brightness in a month. This sets an absolute constraint on the size of the source. The logic is simple but profound. Imagine the emitting region suddenly brightens. Light from the far side of the region must travel farther to reach us than light from the near side. This creates a time delay. If the region is 1 light month across, the delay is 1 month. And we see the change spread out over that time. If we observe a change that happens in less than a month, the region must be smaller than 1 light month. This technique, called light travel time arguments, is one of the fundamental tools astronomers use to measure the sizes of distant objects. The position of the quasar within the universe also affects how we study it. The light must pass through intervening space, crossing regions filled with diffuse gas and occasional concentrations of matter. These foreground clouds absorb certain wavelengths, leaving imprints in the spectrum. By identifying these absorption features, astronomers can map the distribution of matter between us and the quasar, tracing the structure of the cosmic web along the line of sight. This technique has revealed that the space between galaxies is not empty, but filled with a dilute intergalactic medium that plays a key role in galaxy evolution. The intergalactic medium is like a cosmic fog, invisible to the naked eye, but detectable through its effects on light passing through it. It is made mostly of hydrogen, heated to temperatures of tens of thousands of degrees, spread so thinly that a cubic meter might contain only a handful of atoms. Yet across billions of light years, even this tenuous gas leaves its mark. This gas is the leftover material from the formation of galaxies. When galaxies formed, they captured most of the nearby gas, but not all of it. Some remained spread out between the galaxies, slowly cooling, occasionally stirred by winds and jets from active galactic nuclei. This intergalactic medium serves as a reservoir, slowly feeding galaxies over time. It also acts as a tracer of cosmic structure, flowing along the filaments of the cosmic web and pooling at the nodes. By studying absorption lines in quasar spectra, astronomers can map this gas and trace the web itself. At this scale, the quasar serves as a beacon, illuminating not only its own properties, but also the universe through which its light travels. Every photon carries information about the conditions it encountered along the way. The redshift records the expansion of space. The absorption lines trace the distribution of gas. The brightness reveals the power of the central engine. Together, these observations build a comprehensive picture of the quasar and its place in the cosmos. Quasars are thus tools as well as subjects. They illuminate the universe for us. They probe the intergalactic medium. They trace the cosmic web. They serve as lighthouses, allowing us to map the structure of space and time across billions of light years. The metaphor of lighthouses is apt. Just as lighthouses on Earth help sailors navigate, quasars help astronomers navigate the universe. They mark the locations of the densest nodes in the cosmic web. They provide reference points for measuring distances and tracking the expansion of space. They illuminate the gas between galaxies, making visible what would otherwise remain hidden. Without quasars, our understanding of the large-scale universe would be far more limited. The distance of the quasar also places it in a specific epoch of cosmic history. The universe at that time was roughly 1/5 its current age. Star formation was near its peak. Galaxies were colliding and merging more frequently, and the rate at which black holes accumulated mass was higher than it is today. These conditions provided the ideal environment for growing supermassive black holes. The quasar we observe is a snapshot of that active era, frozen in time by the finite speed of light. Every observation is an act of archaeology. We dig through layers of time, uncovering the history of the universe one photon at a time. The quasar shows us what the cosmos was like when it was young, when things were different, when the future was still uncertain. This archaeological perspective is one of the most remarkable aspects of astronomy. We cannot travel back in time. We cannot revisit the past, but we can observe it. Every time we look at a distant object, we see it as it was when the light left it, not as it is now. This allows us to study the history of the universe directly, watching how galaxies formed, how stars evolved, how structures grew. Astronomy is history written in light. Looking at this quasar from Earth, we see not the object as it exists now, but as it existed billions of years ago. The black hole at its center may have grown larger since then, or it may have exhausted its fuel and dimmed. We cannot know its present state, only its past. This temporal displacement is a fundamental feature of astronomy. Every observation is a glimpse into history. The farther we look, the deeper we see into the past. For the quasar hosting the largest black hole ever measured, that past reveals a universe in the midst of transformation, with matter flowing along the cosmic web and black holes reaching unprecedented scales. Time becomes elastic at cosmic distances. The present is inaccessible. We can only see what was, and what was tells us about how things came to be. The quasar's light is a fossil, preserved across billions of years, carrying information from an era long past. Fossils tell stories. They reveal what life was like in ancient times. They show us creatures that no longer exist, environments that have vanished, processes that have ceased. The light from distant quasars is similar. It is a fossil record of the early universe, preserved not in rock but in photons, telling us about a time when the cosmos was very different from today. The position of this quasar in the universe is therefore not just a coordinate in space, but a marker in time. It tells us when and where such extreme objects could form. It confirms that the conditions necessary for growing the largest black holes existed in the early universe. And it provides a target for ongoing study, a distant beacon whose light carries the signature of processes operating at the edge of what gravity and matter can achieve. From this vantage point, billions of light years away, we can only observe, but what we observe is extraordinary. A quasar shining with the power of hundreds of trillions of suns, driven by a black hole whose mass challenges our understanding of how such objects come to be. Moving inward from the position of the quasar in the universe, we arrive at its host galaxy. This is the structure within which the central black hole resides, the place where stars, gas, and dust surround the luminous core. The host galaxy is vast, spanning hundreds of thousands of light years. Yet it is dominated by the energy released from the black hole at its center. The relationship between the two is fundamental. The galaxy provides the material that feeds the black hole, and the black hole, in turn, regulates the evolution of the galaxy through the energy and momentum it injects into the surrounding environment. This is a symbiotic relationship, though not a peaceful one. The galaxy and its black hole grow together. They shape each other. They influence each other's evolution. Neither can be understood in isolation. The dance between galaxy and black hole is delicate. If the black hole grows too quickly, its feedback can blow away all the gas, shutting off star formation and ending its own growth. If it grows too slowly, it may not be able to regulate the galaxy effectively. The observed correlation between black hole mass and galaxy mass suggests that a balance is usually achieved, with the two growing in lockstep over billions of years. Observations of the host galaxy are challenging because the quasar outshines it by a large margin. The central point of light is so bright that it overwhelms the fainter glow of stars in the outer regions. To study the host, astronomers must carefully subtract the light of the quasar from their images, a process that requires precise measurements and sophisticated techniques. What remains after this subtraction is a faint, extended structure consistent with a massive elliptical galaxy. These are among the largest and most evolved galaxies in the universe, typically containing old stars and little ongoing star formation. Imagine trying to see a candle flame next to a searchlight. That is the challenge astronomers face when studying quasar host galaxies. The central source is so overwhelmingly bright that the surrounding galaxy becomes nearly invisible. Only through careful analysis can the host be revealed. The techniques for subtracting the quasar light are sophisticated. Astronomers build models of the quasar's point spread function, how light from a point source spreads out in the telescope due to diffraction and atmospheric turbulence. They then subtract this model from the image, leaving behind only the extended light from the host galaxy. The process is iterative and requires great care, but when done correctly, it can reveal the structure of the host even in the glare of the quasar. The mass of the host galaxy can be estimated from its stellar light and from the motion of gas and stars within it. For this particular host, the total mass, including dark matter, is likely several trillion times the mass of the Sun. This places it among the most massive galaxies known, fitting the pattern that the largest black holes are found in the most massive hosts. The correlation between black hole mass and host galaxy mass is well established and reflects the shared history of growth. Galaxies and their central black holes evolve together, each influencing the other through cycles of accretion and feedback. This correlation is not perfect, but it is strong. Big galaxies host big black holes. Small galaxies host smaller black holes. The relationship suggests a deep connection between the two, a link forged over billions of years of co-evolution. The origin of this correlation is still debated. Some theories suggest that mergers drive both galaxy and black hole growth simultaneously. Others propose that black hole feedback regulates galaxy growth, creating the correlation. Still others suggest that both grow from the same reservoir of gas, naturally producing the observed relationship. All of these mechanisms likely play a role, and disentangling them is an active area of research. The structure of the host galaxy also provides clues about its formation. Elliptical galaxies like this one are thought to form through mergers of smaller galaxies. When two or more galaxies collide, their gas clouds compress and form stars in intense bursts. The central black holes of the merging galaxies sink toward the center of the newly formed system, eventually coalescing into a single, more massive black hole. This process not only builds up the black hole mass, but also stirs the stellar population, creating the smooth, extended distribution of stars characteristic of elliptical galaxies. Galaxy mergers are violent events, but they unfold over millions of years. Stars rarely collide because space is mostly empty, but gas clouds crash together, shock waves ripple through the system, and bursts of star formation light up the merged galaxy. The central black holes spiral inward, losing energy to the surrounding stars, eventually meeting and merging in a final cataclysm. The merger process is fascinating in its complexity. As two galaxies approach, their gravitational interaction first distorts their shapes, pulling out long tidal tails of stars and gas. Then the galaxies pass through each other, their stars intermixing but rarely colliding. The gas, however, does collide, creating shock waves that compress the clouds and trigger intense bursts of star formation. These starbursts can produce thousands of solar masses worth of new stars each year, far more than the sedate rate of a few solar masses per year typical of normal galaxies like the Milky Way. The host galaxy of this quasar likely formed through multiple such mergers. Its position at a dense node of the cosmic web would have made collisions frequent, providing ample opportunities for growth. Each merger brought not only stars, but also gas, the fuel needed to sustain the quasar's luminosity. The timing of these events is recorded in the ages of the stars and in the structure of the galaxy itself. Older stars dominate the outer regions, while traces of more recent activity may linger closer to the center, though these are hidden by the glare of the quasar. The galaxy is a palimpsest, a manuscript written and rewritten many times. Each merger added a new layer. Each event left its mark. By studying the distribution of stars, their ages, their chemical compositions, astronomers can read the history of the galaxy, deciphering the sequence of events that led to its current state. This idea of the galaxy as a historical record is powerful. Just as geologists study rock layers to understand Earth's history, astronomers study stellar populations to understand galaxy history. Old stars, rich in hydrogen and helium but poor in heavier elements, tell us about the galaxy's youth. Younger stars, enriched with elements forged in earlier generations, tell us about more recent activity. The distribution of these populations traces the galaxy's evolution. The host galaxy also plays a role in shaping the environment around the black hole. Gas within the galaxy is subject to many forces. Gravity pulls it inward, while rotation and turbulence stir it into complex patterns. Star formation consumes some of the gas, while stellar winds and supernova explosions return enriched material to the interstellar medium. Amid these processes, a fraction of the gas finds its way to the center, drawn by the deepening gravitational well. This flow is not smooth or steady, but episodic, driven by the timing of mergers and the availability of cold gas. The galaxy is not a static structure, but a dynamic system. Gas circulates, stars form and die. Material flows inward and outward in complex patterns. The black hole at the center sits at the bottom of a gravity well, waiting to capture whatever material happens to drift too close. Understanding this gas flow is crucial. Not all gas in a galaxy falls into the black hole. Most remains in the outer regions, forming stars or simply orbiting. For gas to reach the center, it must lose both energy and angular momentum. Energy can be lost through collisions and radiation. Angular momentum is harder to shed, typically requiring some kind of redistribution mechanism. Magnetic fields, bars in the galaxy's disk, spiral density waves, all can transport angular momentum outward, allowing gas to spiral inward. The details are complex and still not fully understood. The host galaxy is not isolated from the larger universe. It sits within a halo of dark matter, an invisible structure that extends far beyond the visible stars and dominates the total mass. This halo provides the gravitational framework that holds the galaxy together and determines its interactions with neighboring galaxies. The dark matter distribution is shaped by the history of accretion along the cosmic web, reflecting the same large-scale processes that delivered gas and galaxies to this location over billions of years. Dark matter is the hidden foundation upon which the visible galaxy rests. It cannot be seen, but its presence is felt through its gravitational influence. Without dark matter, the galaxy would fly apart, unable to hold itself together against the centrifugal force of its own rotation. The dark matter halo extends much farther than the visible galaxy, perhaps several times the galaxy's visible radius. Within this halo, smaller dark matter clumps may orbit, remnants of galaxies that were captured and absorbed. These clumps, stripped of their stars and gas, persist as dark satellites, invisible but gravitationally significant. Mapping the dark matter distribution is difficult, but can be done through gravitational lensing, the motion of stars and gas, and simulations based on our understanding of structure formation. Within the host galaxy, the central region is of particular interest. This is where the gravitational influence of the black hole is strongest and where the brightest emission originates. The stars near the center are old and densely packed, moving in orbits shaped by the black hole's gravity. Gas in this region is heated to high temperatures by shocks and by radiation from the quasar, making it visible in X-rays and ultraviolet light. The interaction between the black hole and its immediate surroundings is complex, involving both inflows that feed the black hole and outflows that carry energy and momentum outward. Near the center, the environment is extreme. Temperatures reach millions of degrees, densities are high, magnetic fields are strong. Radiation floods the region, ionizing gas and driving powerful winds. This is not a place where planets could form or life could exist. It is a domain of pure physics, where matter and energy interact in their most extreme forms. If we could somehow observe this region up close, we would see a violent, churning maelstrom. Gas swirls in complex patterns. Shock waves crisscross the disk. Jets of material shoot outward at nearly the speed of light. The glare of radiation is so intense it would instantly vaporize anything nearby. Yet from billions of light years away, all this violence is reduced to a faint point of light, a gentle glow that tells us of processes beyond imagining. The host galaxy also influences how we observe the quasar. Dust within the galaxy can absorb and scatter light from the central source, reddening the observed spectrum and reducing the apparent brightness. By measuring the amount of reddening, astronomers can estimate the amount of dust along the line of sight and correct for its effects. This allows them to infer the true luminosity of the quasar and the properties of the central black hole. In some cases, dust may be concentrated in a disk or torus around the black hole, creating an asymmetry that affects what we see depending on the viewing angle. Dust is both a hindrance and a tool. It obscures the quasar, making observations more difficult, but it also carries information. The way dust absorbs and scatters light reveals its composition, temperature, and distribution. By studying the dust, astronomers learn about the environment surrounding the black hole. Cosmic dust is fascinating in its own right. These are tiny grains, smaller than smoke particles, made of silicates, carbon, and other materials. They form in the outer atmospheres of cool stars and are scattered into space when those stars die. Dust blocks visible light, but glows in infrared, creating a distinctive signature. In star-forming regions, dust shields molecular clouds from destructive radiation, allowing stars to form. Around black holes, dust can partially obscure the central engine, creating what astronomers call obscured quasars. The mass of the host galaxy is also linked to the mass of the central black hole through an empirical relationship known as the black hole to galaxy mass ratio. For most galaxies, the black hole mass is about 1/1000th the mass of the stellar bulge. This ratio holds across a wide range of galaxy types and black hole masses, suggesting that the growth of the two is coupled. For the quasar hosting the largest black hole known, this relationship implies a host galaxy of immense mass, consistent with the observations. This ratio is one of the most intriguing discoveries in modern astronomy. It suggests that black holes and galaxies are not independent, but linked by some fundamental process that regulates their growth. The exact nature of this process is still debated, but feedback from the black hole is thought to play a key role. One possible explanation is that black holes regulate their own growth through feedback. As the black hole accretes and shines as a quasar, the energy it releases heats the surrounding gas, preventing it from cooling and forming stars. This also prevents more gas from falling into the black hole, slowing its growth. The black hole grows until it becomes bright enough to shut off its own fuel supply, at which point it settles into a mass that is proportional to the galaxy's mass. This self-regulation could explain the observed correlation. The host galaxy is also a site of ongoing evolution. Though the quasar phase represents a period of intense activity, it is only one chapter in the galaxy's history. Over time, the supply of gas will dwindle. The quasar will fade, and the galaxy will settle into a quieter state. The stars will continue to orbit, gradually losing energy through interactions and stellar evolution. The black hole will remain, its mass unchanged, unless new material arrives. The structure of the galaxy will slowly relax, smoothing out irregularities left by past mergers. Galaxies have life cycles, just as stars do. They are born through the gradual accumulation of matter. They grow through mergers and accretion. They age as their star formation slows. And they eventually settle into a quiet retirement, their gas exhausted, their stars old. The quasar phase is a fleeting moment in this long story, a brief period of brilliance before the galaxy fades. The life cycle of a galaxy spans billions of years. Young galaxies are blue, full of hot young stars, actively forming new stars from abundant gas. Middle-aged galaxies like the Milky Way have slowed their star formation, settling into a more sedate existence. Old galaxies, the massive ellipticals, have largely stopped forming stars, their gas exhausted or heated to the point where it cannot cool and condense. The quasar phase typically occurs during periods of rapid growth, often triggered by mergers when fresh gas is delivered to the center. Once the gas is consumed or blown away, the quasar fades and the galaxy enters its twilight years. At this stage of the inward journey, the host galaxy serves as the context for the black hole. It is the reservoir of material, the stage on which the drama of accretion plays out, and the structure shaped by the energy released from the center. Understanding the host is essential for understanding the black hole. The two are not separate entities, but components of a single system, each dependent on the other for its evolution. The galaxy gathers matter from the cosmic web. The black hole processes that matter and releases energy, and the cycle continues, driven by gravity and shaped by the history of the universe. The galaxy and the black hole are partners in a cosmic dance. They influence each other, they grow together, they shape each other's futures. Understanding one requires understanding the other. This partnership is one of the fundamental insights of modern astrophysics. We used to think of galaxies and black holes as separate phenomena, but we now understand that they are intimately connected, co-evolving over cosmic time. The black hole is not an add-on to the galaxy, but an integral part of its structure. The galaxy is not just a host for the black hole, but an active participant in its growth. Together, they form a unified system, a cosmic engine powered by gravity. The host galaxy of TON 618 is therefore more than a backdrop. It is an active participant in the story of the largest black hole ever measured. Its mass, structure, and history all contribute to the conditions that allowed the black hole to grow so large, and its ongoing evolution will determine the future of the system. From this perspective, the galaxy is not just the home of the black hole, but the reason it exists at all. Moving deeper into the system, we encounter the accretion disk. This is the swirling ring of gas and dust that surrounds the black hole. It is here that matter begins its final descent. Here, that gravitational energy is converted into light, and here that the quasar's brilliance originates. The accretion disk is not a solid structure, but a flow. Material spirals inward, orbiting faster as it gets closer to the black hole. Friction between neighboring layers heats the gas to millions of degrees, causing it to radiate across the electromagnetic spectrum. The accretion disk is where the abstract becomes visible. Without it, the black hole would be invisible, a dark void in space. But with it, the black hole becomes one of the brightest objects in the universe. The disk transforms gravitational potential energy into light, making the invisible visible. The transformation of gravitational energy into radiation is one of nature's most efficient power sources. As gas falls inward through the disk, it loses gravitational potential energy. This energy has to go somewhere, and it goes into heat and radiation. The deeper the gas falls into the gravitational well, the more energy is released. Near the black hole, where gravity is strongest, the energy release reaches its peak. This is why the inner parts of accretion disks are so hot and bright. The accretion disk around such a massive black hole is enormous. It extends for billions of kilometers, larger than the orbit of Pluto. Yet from billions of light years away, it appears as a single point of light. Its structure can only be inferred from the spectrum and variability of the quasar. Different regions of the disk emit different wavelengths. The outer parts, cooler and slower, radiate in infrared and optical light. The inner parts, hotter and faster, emit ultraviolet and X-rays. By analyzing the spectrum, astronomers can map the temperature and density profile of the disk, reconstructing its structure without ever seeing it directly. The disk is stratified by temperature, like the atmosphere of a planet. The outer regions are cool, merely thousands of degrees. As you move inward, the temperature rises. 10,000 degrees, 100,000 degrees, near the center, millions of degrees. Each temperature corresponds to a different color of light, creating a rainbow of emission from the disk. This temperature stratification creates what astronomers call a multicolored disk spectrum. The outer regions emit red and infrared light. The middle regions emit optical and ultraviolet. The inner regions emit X-rays. When combined, these create a characteristic spectrum that peaks in the ultraviolet, a signature feature of quasars. This big blue bump, as it is called, is direct evidence of a hot accretion disk surrounding a supermassive black hole. The disk is fed by gas from the surrounding galaxy. This gas may come from stellar winds, from clouds in the interstellar medium, or from the tidal disruption of stars that venture too close to the black hole. Once captured by the black hole's gravity, the gas does not fall straight in. It carries angular momentum, a measure of its rotation. This prevents a direct collapse and instead forces the gas into orbits. The orbits gradually decay as friction and magnetic fields extract angular momentum, allowing the gas to spiral slowly inward. Angular momentum is a conserved quantity, a fundamental property of rotating systems. Gas cannot simply fall straight into the black hole because it is rotating. Instead, it must lose its angular momentum gradually, spiraling inward over time. This slow descent is what creates the accretion disk and allows the gas to heat up and radiate. Think of it like water draining from a bathtub. The water doesn't fall straight down the drain. Instead, it forms a whirlpool, spiraling inward as it descends. The whirlpool exists because the water has angular momentum. Even a tiny initial rotation, too small to notice, is amplified as the water gets closer to the drain. The same principle applies to gas falling into a black hole, but on a far grander scale. As the gas descends, it heats up. The temperature rises because the gravitational potential energy of the infalling material is converted into thermal energy. In the outer disk, the temperature is a few thousand degrees, enough to emit visible light. In the middle regions, temperatures reach tens of thousands of degrees, producing ultraviolet radiation. Near the inner edge, closest to the black hole, temperatures soar to millions of degrees, generating X-rays. This stratification of temperature with radius is a defining feature of accretion disks and is directly observable in the quasar spectrum. The disk glows because it is hot, and it is hot because gravity is converting the potential energy of infalling matter into thermal energy. This process is remarkably efficient. A small amount of mass falling into a black hole can release more energy than nuclear fusion in stars. This is why quasars are so bright. The detailed physics of how the disk heats up involves viscosity, the internal friction of the gas. As different layers of the disk orbit at different speeds, they rub against each other, generating heat. This viscosity is not like the viscosity of honey or motor oil. In the disk, it is likely generated by turbulence and magnetic fields, processes that are still not fully understood. But the result is clear. The disk heats up from the inside, glowing brightly as it converts gravitational energy into light. The disk is also highly turbulent. Magnetic fields thread through the gas, generating instabilities that create clumps and spirals. These structures stir the disk, transporting angular momentum outward and allowing mass to flow inward. The turbulence is not random, but organized by the interplay of rotation, magnetism, and gravity. The result is a dynamic, churning flow that releases energy at every scale. Observations of variability in the quasar's brightness reveal the chaotic nature of the disk. Fluctuations occur on time scales, from hours to years, reflecting changes in the rate at which material reaches the inner regions. Turbulence is the key to understanding how accretion disks work. Without it, the disk would be stable, and gas would not lose angular momentum efficiently. With it, the disk becomes a dynamic system, constantly churning, mixing, and transporting material inward, while carrying angular momentum outward. The mechanism generating this turbulence is thought to be the magnetorotational instability, a process discovered through computer simulations in the 1990s. When magnetic fields thread through a rotating disk, they become unstable, creating turbulence that stirs the gas and transports angular momentum. This discovery was a major breakthrough in accretion disk theory, explaining how disks can accrete efficiently. The turbulence generated by this instability is not smooth or uniform, but creates eddies and whirls at all scales, from the size of the disk down to tiny fluctuations. The inner edge of the accretion disk is set by the black hole itself. At a certain radius, the orbits become unstable and the gas plunges inward, crossing the event horizon and disappearing from view. This radius, known as the innermost stable circular orbit, depends on the spin of the black hole. For a non-rotating black hole, it lies at 3 times the radius of the event horizon. For a rapidly spinning black hole, it can be much closer. The exact location of this boundary affects the spectrum of the disk, particularly the shape of the ion emission line, a key diagnostic used to measure black hole spin. The innermost stable circular orbit marks the boundary between the disk and the plunge region. Inside this orbit, there are no stable circular paths. Gas entering this region spirals rapidly inward, crossing the event horizon in a matter of seconds or minutes. This is the point of no return, the last stop before oblivion. The concept of the innermost stable orbit is unique to general relativity. In Newtonian gravity, orbits can exist at any radius, no matter how close to the central mass. But in general relativity, space-time is so curved near a black hole that orbits become unstable below a certain radius. Inside this radius, even light cannot orbit. The gas plunges inward, accelerating as it falls, radiating furiously in its final moments before crossing the horizon. The accretion disk is not only a source of light, but also a source of structure. The intense radiation it emits heats the surrounding gas, creating pressure that can drive outflows. These outflows take the form of winds that stream away from the disk, carrying energy and momentum into the host galaxy. Some of the wind material may escape the galaxy entirely, enriching the intergalactic medium with heavy elements. Other material may fall back, recycling through the system. The balance between inflow and outflow is delicate and determines how efficiently the black hole can grow. Outflows are a form of feedback. The black hole feeds on gas from the disk, but in doing so, it releases energy that can blow away the very gas it needs to continue growing. This self-regulating mechanism may explain why black holes do not grow indefinitely, why they reach a certain mass and then slow their growth. These winds can be incredibly powerful. They carry energy at rates comparable to the total energy output of the quasar, and they can reach speeds of thousands of kilometers per second. When these winds crash into the surrounding gas, they create shocks, heating the gas and preventing it from cooling and forming stars. This is one way that black holes regulate star formation in galaxies, a process that has profound implications for galaxy evolution. The disk also interacts with the magnetic field. The gas in the disk is ionized, meaning it carries electric charge. As the gas moves, it drags the magnetic field along, winding it into tight spirals. The magnetic field, in turn, exerts forces on the gas, channeling some of it into narrow jets that shoot outward at nearly the speed of light. These jets are launched from the innermost regions of the disk, close to the black hole, and extend for thousands or even millions of light years. They are among the most powerful phenomena in the universe, capable of heating intergalactic gas and affecting the evolution of entire galaxy clusters. Jets are one of the great mysteries of black hole physics. How can a black hole, from which nothing can escape, produce jets that travel at nearly the speed of light? The answer lies in the magnetic field and the rotation of the disk. These ingredients, combined with the extreme environment near the black hole, can tap into the rotational energy of the system and channel it into powerful, collimated outflows. The exact mechanism of jet launching is still debated. One popular model involves the twisting of magnetic field lines near the black hole. As the disk rotates, it winds up the magnetic field like a spring. The field lines become tightly wound, storing enormous amounts of energy. Eventually, this energy is released, accelerating particles along the field lines and launching them outward in a narrow jet. The process is complex and involves sophisticated physics, including general relativity and magnetohydrodynamics. But the basic picture is becoming clearer. The spectrum of the accretion disk is rich in detail. Emission lines from ionized atoms reveal the composition of the gas and the conditions under which it radiates. Broadened lines indicate motion, with Doppler shifts tracing the rotation of the disk. Asymmetric line profiles reveal the effects of general relativity, as light from the inner disk is redshifted and bent by the black hole's gravity. By fitting models to these spectral features, astronomers can measure the mass of the black hole, the structure of the disk, and even the spin of the black hole itself. Every line in the spectrum tells a story. The width reveals the velocity of the gas. The shape reveals the geometry of the emitting region. The intensity reveals the temperature and density. Together, these features paint a detailed picture of the disk, allowing astronomers to reconstruct its structure and dynamics without ever seeing it directly. The ion line deserves special attention. Ion atoms in the disk are bombarded by X-rays from the corona. This strips away many of their electrons, leaving highly ionized ion atoms. These atoms emit fluorescent X-rays at a characteristic energy, creating a bright emission line in the spectrum. But because the disk is rotating at high speed, and because space-time near the black hole is curved, this line is distorted. The light from the approaching side of the disk is blue-shifted. The light from the receding side is red-shifted. And the light from near the black hole is gravitationally redshifted. The result is a broad, asymmetric line profile that carries the signature of a rapidly rotating disk in curved spacetime. The disk is also subject to instabilities that can cause dramatic outbursts. If the rate of accretion suddenly increases, perhaps due to the arrival of a new clump of gas, the disk brightens. If the rate decreases, it dims. These variations are seen in the light curves of quasars, which show a pattern of flickering on short timescales and longer-term trends. For the quasar hosting the largest black hole, the disk is remarkably stable, maintaining a high level of emission over periods of years. This suggests a steady supply of fuel and efficient transport of material through the disk. Stability is a sign of maturity. Young, rapidly growing black holes often show strong variability as clumps of gas fall in sporadically. Older, more established systems tend to be more stable, fed by a steady stream of material that has been smoothed out by the disk's internal processes. Some quasars show dramatic variability, changing their brightness by factors of 2 or more over periods of weeks or months. Others, like this one, are relatively steady. The difference likely reflects the way gas is delivered to the disk. If the supply is smooth and continuous, the quasar will be steady. If the supply is clumpy and intermittent, the quasar will vary. Understanding this variability helps astronomers understand the processes feeding the black hole. The accretion disk is the engine of the quasar. It is the place where gravitational energy is liberated and where matter is transformed into light. Without it, the black hole would be invisible, a dark void in space. With it, the black hole becomes one of the brightest objects in the universe. The disk is the reason we can study black holes at all. It is the interface between the observable and the unobservable, the region where physics at the extremes can be probed and tested. The disk makes the black hole visible. It converts gravity into light. It transforms the abstract into the observable. Without the disk, black holes would remain theoretical curiosities, impossible to detect or study. With it, they become laboratories for testing our understanding of physics in the most extreme conditions imaginable. At this stage of the inward journey, the accretion disk represents the heart of the quasar's luminosity. It is a vast, swirling structure, glowing with the heat of infalling matter and shaped by the fierce forces of gravity and magnetism. It is also a window into the black hole, revealing through its light the properties of the unseen mass at the center. For astronomers, the disk is both the subject of study and the tool by which the black hole can be measured. Every photon it emits carries information, and every variation in its brightness adds to the story of the largest black hole ever known. Surrounding the accretion disk, though much smaller in extent, is the corona. This is a region of hot, diffuse gas that envelops the inner disk. It is thought to be composed of energetic particles, perhaps heated by magnetic reconnection or shock waves generated in the turbulent disk. The corona is much hotter than the disk itself, reaching temperatures of billions of degrees. At such temperatures, the gas emits primarily in X-rays, adding a high energy component to the quasar spectrum. The corona is mysterious. We know it exists because we observe its X-ray emission, but we do not fully understand how it forms or what maintains its extreme temperature. It may be heated by magnetic fields that snap and reconnect in the turbulent disk, or it may be energized by shock waves generated by the chaotic flow of gas near the black hole. Magnetic reconnection is a process where magnetic field lines break and reconnect in new configurations, releasing enormous amounts of energy. This happens on the Sun, powering solar flares and coronal mass ejections. It likely happens in accretion disks too, heating the corona to extreme temperatures. The exact details are uncertain, but the basic idea is that the tangled magnetic fields in the disk become unstable, releasing their stored energy into the gas and creating the hot corona. The corona is not well understood. Its exact structure, size, and heating mechanism remain subjects of research. What is clear is that it plays a crucial role in shaping the observed light from the quasar. The X-rays produced by the corona illuminate the accretion disk, causing the disk to fluoresce. This fluorescence creates emission lines, particularly the iron line, which is one of the most prominent features in the X-ray spectrum. By studying these lines, astronomers can probe the geometry of the system and measure the relativistic effects near the black hole. The iron line is like a fingerprint. Its shape and position reveal the conditions near the black hole. The line is broadened and skewed by the motion of gas in the disk and by the curvature of space-time. By analyzing its profile, astronomers can measure the spin of the black hole and test the predictions of general relativity. The corona is also variable. Changes in its temperature or density cause fluctuations in the X-ray brightness. These variations can occur on timescales of hours, much faster than changes in the optical light from the disk. This rapid variability reveals the compact size of the corona, which must be small enough for light to cross it within the observed timescales. For the quasar hosting the largest black hole, the corona is still incredibly tiny compared to the scale of the accretion disk, yet it produces a significant fraction of the total energy output. The corona's rapid variability tells us it is small, perhaps only a few times the size of the event horizon. This is tiny on cosmic scales, yet it outshines entire galaxies in X-rays. The concentration of energy in such a small volume is one of the defining features of active galactic nuclei. The interaction between the corona and the disk is complex. Photons from the disk are scattered and absorbed by the hot gas in the corona, gaining energy in the process. This inverse Compton scattering converts low-energy photons from the disk into high-energy X-rays. The spectrum of the quasar, therefore, contains contributions from both the disk and the corona, with the relative strength of each component revealing the balance of heating and cooling in the system. Inverse Compton scattering is a process where high-energy electrons transfer energy to low-energy photons. The electrons in the corona are so energetic that they can boost optical or ultraviolet photons from the disk up to X-ray energies. This creates a second, higher energy component of the quasar's emission. The corona may also be linked to the launching of jets. Some models suggest that the base of the jet coincides with the hottest regions of the corona, where magnetic fields are most tightly wound. If this is the case, then the corona is not just a passive byproduct of accretion, but an active participant in the outflow process. The energy stored in magnetic fields within the corona could be tapped to accelerate particles to relativistic speeds, feeding the jets that extend far beyond the galaxy. The connection between the corona and jets is still uncertain, but if it exists, it would provide a unified picture of how black holes channel energy into different forms. Some energy goes into heating the corona, some goes into driving winds, and some goes into launching jets. All are powered by the same source, the gravitational energy of infalling matter. Observations of the corona are challenging because it emits primarily in X-rays, which require space-based telescopes to detect. Satellites equipped with X-ray detectors have observed the quasar and measured the spectrum of the corona. The data show the expected features, a steep power law continuum with emission lines superimposed. The variability is also consistent with a small, hot region near the black hole. By monitoring these variations over time, astronomers can map the structure of the corona and test models of its formation and evolution. X-ray observations are difficult. Earth's atmosphere blocks X-rays, so observations must be made from space. X-ray telescopes are complex and expensive, but the rewards are worth the effort. X-rays provide a unique window into the hottest, most energetic regions around black holes. The corona also serves as a probe of general relativity. The X-rays it produces are subject to the same gravitational effects as light from the disk. They are redshifted, blue-shifted, and bent by the strong gravity near the black hole. The iron line, in particular, shows a broad, asymmetric profile that can only be explained by emission from a region where space-time is strongly curved. By fitting models to this profile, astronomers can measure the spin of the black hole and test the predictions of Einstein's theory in the most extreme environment available. General relativity predicts that space-time should be curved near massive objects. The closer you get to a black hole, the more extreme the curvature. The iron line from the corona samples this curved space-time, providing a direct test of Einstein's theory in conditions where gravity is strongest. The corona is a reminder that the region around the black hole is not simple. It is a multi-component system with the disk, corona, jets, and outflows all interacting in ways that are still being unraveled. Each component contributes to the overall spectrum and variability of the quasar, and each carries information about the conditions near the black hole. For the quasar hosting the largest black hole known, the corona adds another layer of complexity to an already extraordinary system. Complexity is a hallmark of black hole systems. They are not simple objects with simple properties. They are dynamic, multi-component systems where many different processes occur simultaneously. Untangling these processes, understanding how they interact, is one of the great challenges of modern astrophysics. At this point in the inward journey, the corona marks the transition from the bulk of the accretion disk to the most extreme environment of all, the immediate vicinity of the event horizon. It is a bridge between the observable and the barely observable, a region where temperatures and densities reach values found nowhere else in the universe. The corona is small, hot, and turbulent. Yet it plays a crucial role in the story of the quasar, shaping the light we see and providing clues to the processes that govern the largest black hole ever measured. At the center of this vast system lies the black hole itself. This is the object that defines everything around it. A region of space-time where gravity is so strong that nothing, not even light, can escape. The black hole is invisible, but its presence is unmistakable. It shapes the orbits of stars, heats the accretion disk, powers the quasar, and leaves its imprint on every photon that reaches us. For TON 618, the black hole is the largest ever measured, with a mass exceeding 60 billion times that of the Sun. 60 billion solar masses. It is a number almost beyond comprehension. To put it in perspective, our entire solar system weighs about 1 solar mass. Our galaxy contains about 200 billion stars, averaging perhaps half a solar mass each. This single black hole weighs as much as several hundred Milky Way galaxies. If we could somehow line up 60 billion suns, they would stretch across a distance of many light years. Yet all that mass is concentrated in a region the size of a solar system. The density is incomprehensible. The gravity is overwhelming. This is not just a massive object. It is a fundamental distortion of space-time, a place where the normal rules break down. The mass of the black hole is determined through several methods, all converging on the same extraordinary value. One approach uses the width of emission lines in the quasar spectrum. These lines are broadened by the motion of gas in the accretion disk, which orbits at speeds determined by the black hole's gravitational pull. The faster the gas moves, the more massive the black hole. By measuring the width of these lines and estimating the size of the emitting region, astronomers can calculate the mass. For this quasar, The result is among the highest ever recorded. This method, called reverberation mapping, relies on the relationship between orbital velocity and mass. The faster the gas orbits, the stronger the gravitational pull, and thus the more massive the black hole. By measuring the velocity from the width of spectral lines, astronomers can infer the mass. Another method uses the relationship between the luminosity of the quasar and the mass of the black hole. There is a maximum rate at which a black hole can accrete matter, set by the balance between gravity pulling material inward and radiation pressure pushing it outward. This limit, known as the Eddington limit, depends on the mass of the black hole. By measuring the luminosity of the quasar and assuming it is accreting near this limit, astronomers can infer the mass. Again, the value points to a black hole of unprecedented size. The Eddington limit is a fundamental constraint on black hole growth. A black hole cannot accrete faster than this limit for long periods, because the radiation produced would blow away the infalling gas. By measuring the quasar's luminosity and assuming it is near the Eddington limit, astronomers can estimate the black hole mass. The black hole is not just massive, but also compact. All of its mass is concentrated within a region defined by the event horizon, a boundary beyond which nothing can return. For a black hole of this mass, the event horizon has a radius of about 10 billion kilometers, roughly the size of our solar system, out to the orbit of Neptune. This is vast by terrestrial standards, yet tiny compared to the scale of galaxies. The density implied by this compactness is almost unimaginable. All the mass packed into a volume of space that, from Earth, would subtend an angle far too small to resolve, even with the most powerful telescopes. The event horizon of TON 618 is enormous. If you could stand at the center of our solar system, the horizon would extend beyond Neptune. Yet this vast region is still just a point in the cosmos, invisible and unreachable, sealed by the laws of physics. The existence of such a massive black hole raises profound questions. How did it grow so large? Black holes are thought to form from the collapse of massive stars or from the direct collapse of dense regions in the early universe. But even starting from a stellar mass black hole, reaching 60 billion solar masses would require billions of years of continuous accretion. The universe at the time this quasar shone was only a few billion years old. This leaves a narrow window for growth, requiring efficient accretion and possibly an unusually massive seed black hole to begin with. Growing a black hole this massive in the available time is a challenge. It requires a steady supply of fuel, efficient accretion, and minimal disruption from feedback. Some theories suggest that the black hole may have started from a massive seed, perhaps formed by the direct collapse of a dense gas cloud in the early universe. The growth of the black hole is also limited by feedback. As matter falls in and releases energy, some of that energy is absorbed by surrounding gas, heating it and driving it away. This reduces the supply of fuel and slows the growth. For the black hole to reach such a large mass, it must have overcome this feedback, perhaps by accreting in bursts during periods when the supply of gas was abundant, or by residing in an environment where feedback was less effective. Feedback is both a blessing and a curse. It limits how fast black holes can grow, preventing them from consuming all the available gas. But it also creates the conditions that make quasars visible, converting gravitational energy into radiation that can be observed across the cosmos. The black hole may have grown through mergers as well as accretion. When two galaxies collide, their central black holes eventually sink to the center of the merged system and coalesce. Each merger adds mass, and over billions of years, a series of mergers can build up a supermassive black hole. The host galaxy of this quasar likely experienced many such events, each contributing to the mass of the central black hole. The correlation between black hole mass and host galaxy mass supports this picture, as both grow together through the same sequence of mergers. Black hole mergers are among the most energetic events in the universe. When two black holes coalesce, they release tremendous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. These waves carry energy away from the system, allowing the two black holes to spiral together and merge. The black hole also affects its surroundings in ways that extend far beyond the accretion disk. The energy it releases heats the surrounding gas, preventing it from cooling and forming stars. This feedback mechanism is thought to regulate the growth of galaxies, explaining why the most massive galaxies have stopped forming stars. For the quasar hosting the largest black hole, the feedback is powerful, injecting energy into the host galaxy and possibly into the intergalactic medium. This energy can travel for hundreds of thousands of light years, affecting the evolution of the entire region. Black holes are not just passive objects. They actively shape their environments. They regulate star formation. They heat gas. They drive winds and jets. They influence the evolution of galaxies and the structure of the universe itself. The black hole is also a laboratory for testing fundamental physics. Near its event horizon, the gravitational field is so strong that space-time is severely curved. Light follows curved paths, time runs slower, and the laws of physics are pushed to their limits. General relativity predicts these effects with precision, and observations of the quasar provide a way to test those predictions. The shape of the iron line, the variability of the X-ray emission, and the structure of the accretion disk all depend on the curvature of space-time. By comparing observations with models, astronomers can verify that Einstein's theory holds even in the most extreme conditions. General relativity has passed every test we have thrown at it, but the environment near a supermassive black hole is the ultimate proving ground. If Einstein's theory is going to break down anywhere, it would be here. So far, it has held up perfectly. The black hole is also an enigma. What happens inside the event horizon is unknowable. Once matter crosses that boundary, it is lost to observation. No signal can escape to tell us what occurs within. The interior of the black hole is a region where space-time itself may be singular, a point of infinite density and curvature. Or perhaps quantum effects intervene, preventing the singularity and creating a structure we do not yet understand. These questions remain at the frontier of physics, unanswered and perhaps unanswerable with current tools. The interior of a black hole is forever beyond our reach. We can theorize, we can calculate, we can speculate, but we cannot observe. The event horizon is an absolute barrier, a one-way membrane that allows no information to escape. From the outside, the black hole is defined by its mass, spin, and electric charge. These three properties completely determine its external gravitational field. For astrophysical black holes, the charge is negligible, leaving mass and spin as the defining characteristics. The mass has been measured. The spin can be inferred from the shape of the accretion disk and the iron line, though the measurement is more uncertain. If the black hole is spinning rapidly, it drags space-time around with it, creating a region where even light must rotate with the black hole. This frame-dragging effect is a direct consequence of general relativity and affects the orbits of particles near the horizon. Black holes are remarkably simple objects, described by just a few numbers. Yet these simple parameters hide a universe of complexity in the environment surrounding the black hole. The mass and spin determine everything, from the size of the event horizon to the structure of the accretion disk to the power of the jets. The black hole at the center of TON 618 is not just the largest known, but also a symbol of the extremes the universe can reach. It is a gravitational monster, a cosmic engine, and a window into the most fundamental aspects of reality. It is the culmination of billions of years of growth, fed by the cosmic web and shaped by the history of its host galaxy. And it is the reason we can observe this quasar at all. Without the black hole, there would be no accretion disk, no corona, no jets, and no light to study. The black hole is the anchor of the entire system, the unseen mass that makes the visible possible. Everything we see traces back to the black hole. The quasar's brilliance, the galaxy's structure, the flow of gas along the cosmic web, all are consequences of this single object, this concentration of mass so extreme that it bends space and time around itself. At this stage of the inward journey, we have reached the core of the story. The black hole is both the simplest and the most complex object we can imagine. Simple because it is defined by just a few numbers. Complex because those numbers hide a depth of physics that we are only beginning to explore. For the largest black hole ever measured, the journey ends here, at the boundary where observation gives way to inference, and where the known meets the unknown. Surrounding the black hole is a critical boundary known as the event horizon. This is the point of no return, the invisible edge beyond which nothing can escape, not matter, not light, not information of any kind. For the black hole at the center of TON 618, the event horizon is immense, enclosing a volume roughly the size of our solar system. Yet it is not a physical surface. It is a mathematical boundary in space-time, defined purely by the strength of gravity. Cross this line and the future becomes singular. All paths lead inward. All journeys end at the center. The event horizon is one of the most profound concepts in physics. It represents the ultimate boundary, the point beyond which the universe is forever hidden from view. It is not made of matter or energy. It is made of geometry, a shape carved into space-time itself by the presence of mass. The event horizon is not marked by any change in the structure of space. An object falling toward it would notice nothing unusual at the moment of crossing, at least not from its own perspective. There is no barrier, no wall, no sudden transition, yet to an outside observer, the crossing would appear very different. As the object approaches the horizon, it would seem to slow down, its light red-shifting toward longer wavelengths. Time itself would appear to dilate, with each second for the falling object stretching into minutes, hours, and eventually eternity. The object would never quite seem to reach the horizon. It would freeze at the edge, fading from view as its light becomes too faint and too redshifted to detect. This is one of the strangest predictions of general relativity. Time is not absolute. It depends on where you are and how you are moving. Near a black hole, time behaves very differently for different observers. What seems like a moment to one observer can seem like an eternity to another. This difference in perception is a consequence of general relativity. Time and space are not absolute, but depend on the observer's frame of reference. Near the event horizon, the curvature of space-time becomes so extreme that time for a distant observer behaves very differently from time for a falling observer. The falling observer crosses the horizon in finite time and continues inward. The distant observer sees the fall slow to a halt, asymptotically approaching the horizon but never quite arriving. Both perspectives are correct within their own frames. There is no contradiction here, only a reminder that reality is more subtle than our everyday experience suggests. Time and space are intertwined, woven together into a four-dimensional fabric that curves and flexes under the influence of mass and energy. The size of the event horizon is proportional to the mass of the black hole. For a non-rotating black hole, the radius of the horizon, called the Schwarzschild radius, is given by a simple formula. For the black hole in this quasar, that radius is about 10 billion kilometers. For a rotating black hole, the horizon is slightly smaller, and its shape becomes oblate rather than perfectly spherical. The exact size and shape depend on the spin of the black hole, a property that can be inferred from observations of the accretion disk. The horizon's size scales linearly with mass. Double the mass, double the radius. This simple relationship masks the profound implications. A black hole this massive has a horizon larger than many solar systems, yet all that mass, all 60 billion suns worth, is concentrated in a region smaller than the orbit of a single planet. The event horizon also defines the boundary between the observable and the unobservable. Everything outside the horizon can, in principle, send signals to distant observers. Everything inside cannot. This makes the horizon the ultimate limit of observation. We can study the gas spiraling toward the horizon. We can measure the light it emits. We can infer the properties of the black hole from how that light is distorted, but we cannot probe the interior. The horizon is an information barrier, a one-way membrane that allows matter and light to enter but not to leave. The horizon is a cosmic sensor, hiding the black hole's interior from the rest of the universe. Whatever happens inside remains forever secret. This one-way nature of the horizon is absolute. Once crossed, there is no return. No signal, no particle, no information can ever escape. The horizon is also the place where energy is extracted from the black hole. In a process known as Penrose extraction, energy can be drawn from the rotation of the black hole by carefully designed interactions near the horizon. Though this process is not directly observed, it is thought to play a role in powering jets from rotating black holes. The energy comes not from the mass of the black hole, but from its spin, and the horizon is the interface where this energy can be accessed. The Penrose process is a theoretical mechanism for extracting energy from a rotating black hole. It relies on the fact that near a spinning black hole, there is a region called the ergosphere, where space-time is dragged along with the black hole's rotation. In this region, it is possible to extract energy from the black hole's spin. For quasars, the event horizon is the sink into which all the infalling matter ultimately disappears. The accretion disk surrounds the horizon, orbiting at high speed and radiating as it spirals inward. But once the gas crosses the horizon, it is gone. It contributes to the mass of the black hole, but emits no further light. The quasar's brightness comes entirely from material outside the horizon. This is why quasars that host the most massive black holes are brilliant. They sit on the edge of darkness, where gravity is strongest and radiation is most efficiently released. The brightest quasars are those where gas is spiraling inward at the highest rate, releasing enormous amounts of energy just before crossing the horizon. The horizon itself is dark, invisible, but the region just outside it is the brightest place in the universe. The horizon is both the end point of matter and the source of observable light. For astronomers, the event horizon is not just a theoretical construct, but a measurable scale. Its size can be calculated from the observed mass of the black hole. Its presence can be inferred from the behavior of surrounding gas. The existence of a horizon is also one of the strongest confirmations of general relativity, showing that massive objects collapse not into hard surfaces, but into regions defined only by geometry. Every quasar spectrum that reveals broadened lines and relativistic effects is indirect evidence that such horizons exist. We have never seen an event horizon directly, except for the shadows cast by nearby black holes imaged by the Event Horizon Telescope. But the evidence for their existence is overwhelming. The behavior of gas near black holes, the shape of spectral lines, the efficiency of energy conversion, all point to the presence of an event horizon. In the case of the largest measured black hole, the scale of the horizon is pushed to extremes, expanding the limits of what is known to exist. The horizon also raises fundamental questions about the fate of information and the nature of physical laws. While these questions extend beyond direct observation, the event horizon of such a massive black hole provides the most dramatic stage on which they can be asked. What can be said with certainty is that the horizon is real in observational terms. It defines the edge of emission, the cutoff beyond which no photon can reach us, and the absolute sink into which all infalling matter vanishes. The event horizon is where physics becomes philosophy. What happens to information that crosses the horizon? Is it lost forever? Or is it somehow preserved? These questions touch on the deepest issues in theoretical physics, connecting general relativity and quantum mechanics in ways we do not yet fully understand. At this stage of the inward progression, the event horizon marks the culmination of all preceding processes. Gas drawn from the cosmic web, funneled through the galaxy, filtered by dust, energized in the accretion disk, and heated in the corona, finally disappears through this invisible boundary. The light that allows the quasar to be seen is generated just outside. But once the horizon is crossed, the trail ends. It is the natural endpoint of matter in the gravitational field of the largest black hole ever recorded. The defining edge where the observable universe yields to the unobservable interior. Inside the boundary marked by the event horizon, light itself cannot escape. Yet just outside it lies the photon sphere, a peculiar region where gravity bends light into closed orbits. At this radius, photons can circle the black hole multiple times before either falling inward or escaping outward. For a black hole as massive as the one at the center of this quasar, the photon sphere extends across a distance larger than the orbit of Earth around the Sun, a vast ring of potential light paths held captive by gravity. The photon sphere is where light does the impossible. Normally, light travels in straight lines, but near a black hole, space-time is so curved that straight lines become circles. Photons orbit the black hole like planets orbit a star, held in place by gravity alone. Although no telescope can directly resolve such a feature at billions of light years, its presence is revealed in the way light from the accretion disk is distorted and magnified. The photon sphere acts as a mirror of space-time, showing the consequences of extreme curvature in a region that still communicates with the outside world. Light that grazes this region can loop around the black hole more than once, creating a series of increasingly faint echoes. Each orbit delays the photon, stretching its arrival time relative to light that travels directly outward. This delay imprints subtle features in the observed variability of the quasar, signatures that astronomers can detect in X-ray reverberation mapping. These echoes are faint, but they are real. They provide a unique probe of the environment near the black hole, allowing astronomers to map the structure of the accretion disk and corona with unprecedented precision. Although the signals are faint at such enormous distances, the physics ensures they exist, and their presence confirms the predictions of general relativity. The photon sphere represents the last frontier of visibility before complete darkness. The geometry of the photon sphere also defines the silhouette of the black hole. To an observer, the boundary between light that escapes and light that falls inward creates a shadow, a dark disk outlined by the glow of the inner accretion disk. Nearby black holes, such as those imaged by the Event Horizon Telescope, show this shadow directly. a circular shape carved into surrounding radiation. The shadow of a black hole is not the black hole itself, but the region where light is so strongly bent that it cannot escape. It is larger than the event horizon, encompassing both the horizon and the photon sphere. The shadow is what makes black holes visible, paradoxically revealing them through their absence. For the quasar that hosts the largest black hole known, the same principle applies on a far grander scale. Though the distance makes direct imaging impossible, the mathematics is exact. The photon sphere traces the visible edge, and the shadow it defines would be the largest of any black hole yet measured. The photon sphere is also a reminder that space-time near a black hole is not intuitive. Photons, which normally travel in straight lines, are forced into curves so extreme that they can orbit like planets. These orbits are unstable, meaning that even the smallest perturbation will send the photon inward or outward. But for an instant, light itself becomes trapped in gravity's grip. Light orbiting a black hole is a testament to the power of gravity to reshape reality. The rules we take for granted, the assumptions that guide our everyday experience, break down completely in this extreme environment. This peculiar condition has no counterpart in ordinary experience and exists only in the vicinity of massive black holes. The fact that such orbits can exist at all underscores how profoundly general relativity reshapes the structure of space. As matter falls inward toward the horizon, it continues to radiate until the last moment. And this light interacts with the photon sphere. Some photons are bent into circular paths, while others are deflected outward, creating patterns of distortion in the observed spectrum. Every photon emitted near the black hole runs the gauntlet of curved space-time. Some escape to distant observers, some fall into the black hole, and some, briefly, orbit before deciding their fate. The broad wings of emission lines, the skewed profiles of iron features, and the asymmetry of variability curves are all consequences of photons navigating the curved space-time of this region. For astronomers, these distortions are not nuisances, but data, offering the only means of studying conditions near the horizon of a black hole. The limits of observation are set here. Beyond the photon sphere, no photon can provide information because once light is trapped, it cannot escape without being redirected outward. The observable universe ends at this radius, with everything inside concealed by gravity. The photon sphere marks the boundary of what we can know. Beyond it lies the event horizon, and beyond that, the unknowable interior of the black hole. Everything we learn about black holes comes from the region outside the photon sphere, from the light that manages to escape. For the quasar connected to TON 618, this means that all we know comes from regions outside the photon sphere. We can measure the inflows, the emissions, the distortions, but not the interior. What happens within remains hidden, sealed by the fundamental structure of space-time. The photon sphere is also central to future tests of physics. The shape of the shadow it defines, the timing of echoes produced by looping photons, and the precise bending of light all depend on the validity of general relativity. Future observations will push these tests to new limits. As our instruments improve, we will measure the shadows of black holes with greater precision. We will detect fainter echoes. We will probe the photon sphere in unprecedented detail. And with each measurement, we will test Einstein's theory more rigorously. If alternative theories of gravity differed from Einstein's predictions, the photon sphere would betray those differences. In this way, the quasar's light becomes not only a record of accretion, but a test of fundamental law. The larger the black hole, the clearer the test. and none is larger than the subject of this study. From Earth, astronomers capture only the integrated spectrum of the quasar, yet encoded in that light are the effects of photon orbits, gravitational delays, and relativistic shifts. Every spectrum is a treasure trove of information. Hidden within the wavelengths and intensities are clues to the black hole's mass, spin, and environment. Astronomers are detectives, piecing together the story from fragments of light that have travelled billions of years to reach us. By analysing these features, they extract the maximum information possible about the innermost region. The picture that emerges is consistent across all observations. A central black hole of unprecedented mass, surrounded by an accretion disk, topped by a corona, possibly launching jets, and bounded by an event horizon and photon sphere that dictate the limits of observation. The quasar's brilliance is the outward manifestation of processes taking place just outside those boundaries. All the pieces fit together. The cosmic web provides the fuel. The galaxy channels it inward. The accretion disk converts gravitational energy into light. The corona adds high-energy radiation. And the black hole sits at the center, invisible but omnipresent, shaping everything around it. At this final inward step, the photon sphere marks the end of the descriptive path. Beyond it lies the horizon, where no light escapes and no measurement can be made. The story of TON 618 ends here, not because the object ceases to exist, but because physics sets a natural frontier. Light cannot tell us what happens inside, and so the narrative concludes at the edge of observation. What remains is the recognition that all we know of the largest black hole ever measured comes from the photons that escape this final barrier, carrying with them the imprint of curved space-time and the power of gravity at its most extreme. We have travelled from the largest scales to the smallest, from the cosmic web spanning billions of light years to the photon sphere just beyond the event horizon. At every step, we have found structures shaped by gravity, processes driven by energy, and mysteries that challenge our understanding. TON 618 stands as a monument to the extremes of nature, a cosmic giant that pushes the boundaries of what we thought possible. And yet, it is not an anomaly. It is a natural consequence of the laws that govern the universe. Gravity, time, space, and energy, all working together to create something extraordinary. The largest black hole ever measured is not just a curiosity. It is a window into the fundamental workings of the cosmos, a laboratory for testing our deepest theories, and a reminder that the universe is far stranger and more wonderful than we ever imagined.